Hi everyone, today we are looking at some applications of integration. You've learnt how to anti-differentiate or integrate things by hand and using your calculator. So now we're going to look at a couple of applications that you might come across in the exams and SACs. So the first one we're talking about is the average value of the function. So when we're talking about this, we have a specific formula that you can see over here. So the average value of a function f for an interval from a to b, and you'll always be given an interval, is defined as this particular formula here. Now, unfortunately, this formula is not on the formula sheet. So that means that you do need to make sure it's in your bound reference, and ideally that you memorize it so you'll know what's going on in exam 1. So let's talk about what this actually means. For a particular graph, so let's draw a particular graph, any particular graph f of x. So here's a particular graph here, I'll call this the graph f of x. And if we are defining this graph and we want to find the area underneath between A, so let's say here's point A, and here's point B. We can calculate the area underneath this region using our formulas that we've done before. So if I wanted the area underneath there, we would get the integral from a to b of f of x dx. Okay? We all know that formula. We've used it before. When we want to calculate the average value, we're asking what is the y value? So when we're doing average value, it's always the average of the y value, or we can think of it of the average as the dependent variable. What is the average value of this function is where do I draw a line such that if I was to draw a particular line, the area of this rectangle in this blue space here is equal to the yellow area. So this corresponding y value here is the average value of the function, and we're trying to choose a value, a y value here, such that the area of this blue rectangle is equal to the yellow area shaded under the curve. For that to happen in this case, it means that this region in here, the area above my average value line, is going to have to be equal to this area here. So we're completing that whole rectangle there. You have to be careful when we're looking at these questions. It has been common in exams for people to be mixed up with average rate of change, which if we remember the average rate of change is our y2 minus y1. It's essentially our gradient formula to calculate the average rate of change between 2 points, whereas the average value, and they won't often use the word value, they could say things like work out the average height or the average of whatever the particular question is giving. When we want the average value, that's when we use this formula here. So you've got to be careful because there's 2 ways we could use the word average. For our average rate of change, the only words that we're going to use for this one here are either average rate of change or they might say average gradient. Okay? Any other time we see the word average, we'll be talking about the average value. So let's actually look at some examples and see how we go about solving these questions. So here we want to calculate the average value of the function and sketch the corresponding line on the graph. So as long as we know our formula, it's quite easy. Our formula, average value, if we remember, our formula was 1 over b minus a, the integral from a to b of negative x minus 2 squared plus 4 dx. If I substitute values into this, I will get 1 over, b is my bigger value, we're going over the interval from 0 to 4, and our values here, we put our smaller one at the bottom terminal and our larger value at the top, and we have our particular function here. These questions have been seen on exam 1 and on exam 2, so you could need to do this by hand, or you might be able to do it using a calculator. If we're solving this without a calculator, let's do this one without. When I anti-differentiate here, our rule for anti-differentiating a linear function to a power is that I add 1 to the power, I divide by the power, and I also divide by the derivative of the inside. The derivative of x minus 2 is just 1. Plus, if I anti-differentiate 4, we get 4x. And this is between 0 and 4. So now if we start substituting in values, we have a quarter. We sub in our top terminal, so I will get negative. 4 minus 2 gives me 2 cubed over 3, plus 4 times 4 is 16. Then we substitute in our second terminal. So when I substitute in 0, I will get negative. 0 minus 2 is negative 2 cubed over 3 plus 0. We do need to be able to simplify this. Remember, knowing how to work with fractions is assumed knowledge. You could absolutely be asked to do that in exam 1 without a calculator. So if we're simplifying what we've got going on here, our negative remains out the front. 2 cubed is the same as 8 over 3, plus, let's write 16 in terms of the same denominator as well. If I want it to be over 3, I multiply 16 by 3, which gives me 48. Here I've got negative 3 in the denominator. Negative 2 cubed is negative 8, but I've got a negative out the front as well. Those 3 negatives make it end up being negative still. So I will have 1 over 4 times negative 8 plus 48 minus 8 is going to give us 32. And simplifying this, we will get 8 over 3, or 2 2/3. So the average value of our function there is 2 2/3. If we sketch the corresponding line, remember the average value gives us a y-intercept, so 2 2/3 will probably be somewhere around here. So if we sketch that line here, that's the average value there at 2 2/3. If we imagine, let's visualize this. Remember, we're saying that the area under the curve, under the parabola, is equal to the area under the box drawn there. So what that means is that we're imagining if I was to cut up this section up the top here, if I was to cut it up, I could fit in these missing sections down here, so that the area under the red rectangle would be the same as the area under the original parabola. Let's have a look and see another example. So let's just have a look at another. So in our second example, we are now doing the same thing, but we've got a different function here. Average value, so we're using the same formula that we were doing before. It's going to be 1 over our b value, which is 4, minus the a value, which is negative 1. The integral from our a value is the smaller value up to the b value there of the function dx. Now, because this one asks us for the value correct to 2 decimal places, at this point we can type it into our calculator. So if you switch your CAS calculator on, enter this into the main menu. The integral sign can be found in Math 2. And if we enter this into the CAS calculator, we will get an answer of 5.43 as the absolute value. If we're drawing that on the line, 5.43, it's going to be just above 5. So we're wanting this just, excuse the fact that my line is not overly straight. If you've got a ruler, that will obviously help. Here is our area of this rectangle. So that's the average value, and what we're saying is that this area under this blue rectangle here would be the same as the area under this whole curve here. That's what we're imagining, okay? That it would be the same as that area under there. And hopefully, if we're looking at this as a way of visualizing it, we can see that this area here even looks like it's the same size and same shape as this area here. So the blue line along the top here represents our average value of the function. If we go on and have a okay, let's look at our final example of this kind. If you haven't done this already, please pause the video here, try yourself, check that you're on the right track, and then you can restart and you can check how you're going. Alright, so to find our average value, we set up our integral. We're wanting to go, before that, we need the start of our fraction. So we are going to say 1 over b minus a, which is 12 minus 0 in this case, integral from our a value to our b value of this particular function dx. As I mentioned before, it is a good idea to try this both by hand and on your calculator, because this could be in tech-free assessments or in tech-active assessments. Let's try this one by hand. We add 1 to the power and divide by the power, and add 1 to the power here. And now we need to substitute in our terminals. If we sub in our first value of 12, we will get negative 12 squared over 8, plus 2 times 12 is 24, minus we sub in our second terminal, which will just give us 0 plus 0. In order to simplify this, the easiest way that I can suggest is to first expand, multiply 1 over 12 by everything inside the brackets. If I multiply 1 over 12 times negative 12 squared over 8, the 12s will cancel out and I will just get negative 12 over 8. 1 over 12 times 24 will just give me plus 2. We can simplify this fraction to give us negative 3 over 2, and we end up with an answer of a half. So now if I'm wanting to visualize where this is, I can find 1 will be about here, so half will be down here. We draw a line to represent that average value. Okay, so here's a line here. We can visualize this in a couple of ways. Notice the average value does take into account the negative area. So the area in this red rectangle here needs to be equal to the signed area. Okay, it's going to be equal to the signed area. Or another way of thinking about it is that this area in this first section here is going to be equal to this area in this second section, in this second triangle here. That's another way we can think about it there. Let's have a look at one final type of example in this particular situation. Okay, so looking at this next option here, in this case we're saying h is a function with an average value of negative 1, and we need to figure out which graph this could be. So if I'm drawing the line negative 1 along here, I'm saying that I want the area in this blue rectangle to be equal to the area under the curve. Hopefully you can see that is not going to be the same. The other way of thinking about it is that I'm saying these areas here, the areas in the blue rectangle, are going to be equal to this area here. They are nowhere near the same, so no, that is not correct. In our second one here, a value of negative 1, our area in the blue rectangle, we are saying that the area under this curve, so we're trying to say that the area in this blue rectangle is going to be equal to the areas under the curve. So the areas under the curve would be this yellow area and this yellow area here. Well, that very likely might be the same. Let's leave this one as a possibility and consider the others before we make a firm decision. -1 will be this part here. So we're trying to say that this area in here, or remember the other way that we're trying to say it is that the areas above are going to be equal to the areas below. Well, if I'm trying to fill in this rectangle here, it is not going to be the same. The areas, we've only got this little bit here, which is below there. That is not going to fill in and match our area here. So that is not correct. Again, -1, we draw a line. So if we're imagining filling this in, this space here already is under the curve. We're trying to say now that this area in here can be filled up with this area here to make them the same area, and that is not the case. -1 will be somewhere quite close in here. And when we saw these other ones, that's also like we're saying we want this area in here to be equal to this area in here. And that does not look to be correct. If you're not sure, we can always calculate the exact area if we wanted to make sure. If we're looking and we're thinking we don't know between these two, well, we can actually do some calculations to become more certain. If we look at this first one here, we've got a triangle here. This triangle has a base, our area of the triangle is equal to half times a base, which is 4, times a height, which is 2. So that would give us an area of 4. We've got 2 triangles, so therefore our total triangle area should be equal to 8. If I want the area of our blue rectangle, that has a length of 8 and a width of 1. Because they are the same areas, this is our correct value here. We could check for this other one if we want to. This value here is probably close to 3. So let's have a look here. If we want the area of our top triangle here, half times a base of 3 times a height of, we've gone from -1 here up to 5. So that's a height of 6, which would give me an area of 9. If I have a look at this area here, the area below, we're going to get area equals half a base. We've gone from 3 to 8, so it's a base of 5, times a height. We've gone from -1 to 10 along here, so that's a length of 9. That's going to give me 45 on 2, which is most definitely not 9. So this one is not correct. So we have, after all of that, found our correct option, which was this second choice here. This kind of question is a very common multiple choice question, so it is definitely worth practicing. Our next example that we're looking at, our next application, is to do with kinematics. You might remember that we talked about this earlier on when we did differential calculus. A few definitions just to remind you. When we talk about position, it's the distance from a fixed point O. So if I had a straight line, here's our O, or our origin, a position where a particle is starting. So if it starts here, its position is 2. Displacement is the change in position relative to a starting point. And again, it has direction. So if we want the change in position, here I've got something that starts, if my particle starts at 2 and then moves to -3, and then after that travels back to 1. So when I'm talking about displacement, the change in position from the start position to the end position is that it's moved to the left by 1. So the displacement in this little diagram here, the position that it ends in is 1. The displacement from the start to the end is -1 because we've moved 1 to the left from 2 to 1 overall. But if I wanted the distance is different again, because the distance we have travelled is we've travelled in this direction here 5 units to the left, and then we've travelled -3 to 1, so that's 4 units to the right. So our distance is 9. So there is a bit of a difference between position, displacement, and distance. Position we always represent using x, and x with respect to time, because particles are in different places at different points in time. Velocity, on the other hand, is the change of position with respect to time. And the sign tells us which way we're going. So a negative sign means we're going to the left, and a positive sign for velocity means we're going to the right. If we work out, just before we get on to speed, with velocity, if we work out the average velocity, we just take our velocity at, not our velocity. Let me try that again, everyone. If we're working out average velocity, it's to do with the displacement. So we take our final position and we subtract our first position, and it's over final time minus first time. This is very similar to the average rate of change that we did back when we did differential calculus. If we want instantaneous velocity, that we get just by differentiating position. That's how we get our velocity. Speed is different. Our speed formula we have is the total distance divided by time. When we work out velocity, we could get a negative or a positive velocity, which tells us if we've been moving to the left or the right. But when we work out speed, we only ever get a positive value. Finally, acceleration. We get acceleration by differentiating velocity. So if we differentiate velocity, that's how we get our acceleration. So just to summarize, if we think we have 3 things that we can use with calculus. We have our position, we have the velocity. So position is represented as x, velocity as v, and acceleration as a. If we differentiate, so in order to get from position to velocity, we have to differentiate. So we differentiate our function. dx dt, it's in terms of t. To get from velocity to acceleration, we have to differentiate our velocity equation. If we are going the opposite way, the opposite idea is going to be to anti-differentiate. So if I integrate a, and it's usually a with respect to t, we get our velocity. If we anti-differentiate velocity, that's how we get position. So we've got to be clear, we're going from position downwards. So going in this direction down here, we differentiate. And I'm going to run out of room here, but going in the opposite direction up here, we anti-differentiate. Let's look at an example. Okay, let's look at a specific example to make a bit more sense of this kinematics idea. So remembering that we have our x is our position, v is the velocity, and a is acceleration. And moving downwards from one to the other, we do it by differentiating. And going back the other way here, we do by anti-differentiating. So to start with, we have for part A, we have our velocity equation, and we want to find its position x in terms of t. So looking at our little information over to the side, that means we have to anti-differentiate. So in order to find x, we are going to anti-differentiate this, or we're going to find the integral of this function here with respect to t. So I add 1 to the power gives me t squared, and dividing by the power over 2, add 1 to the power, and we have to add c. I can simplify. 2 over 2 gives me t squared minus 3 plus c. We need to see if we can find any information to help us find the value of c. Luckily, it does tell us an object starts from point O. So that means this tells us that when t equals 0, so that's from the start, at point O, that the initial position is 0. So we put that information in when t equals 0, x equals 0. So that tells us therefore that c equals 0. So therefore our x equation is t squared minus 3t. Now I know that c is equal to 0 here, but you do need to do this step. It's not enough just to ignore the c, and leave it out. You need to prove to the people reading that you know there is a constant, and you can prove that it's 0. So moving on then, part B, we now want to find its position after 3 seconds. So that means we're wanting to find what is x equal to after 3 seconds when t equals 3. We can substitute it into our equation, which would give us 3 squared is 9, minus 3 times 3 is 9. So that means after 3 seconds, its position is 0 meters. So it must be back where it starts from. To calculate its average velocity, so our average velocity, if we remember the formula, we take our final x value minus our first x value over final t minus first t. So final x value is 0 minus first x value is 0 over t minus t, which actually just gives us 0 meters per second. And that's completely okay. The average velocity is 0 meters per second because we're ending where we started. However, the average speed that we're getting onto, that's going to be something a little bit different. We now need to work out the distance travelled in the first 3 seconds. So we know that our particle starts here at 0 and ends here at 0, but that's not to say that it doesn't go somewhere else in between. In order to know where a particle turns around, because it is going to turn around at some point, it turns around, and when it turns around it stops momentarily, or its velocity is equal to 0. So to know where our particle turns around, we sub velocity equals 0. So I will get 2t minus 3 equals 0. Solving this gives me t equals 3 over 2. That's when it turns around. If I want to know where it turns around, I need to substitute this into my equation, into my position equation, because where is located as a position. So my position equation we worked earlier is this one. So this will give me 3 over 2 squared minus 3 times 3 over 2. So I'll get 9 over 4 minus 9 over 2. If we want a common denominator, that's going to give me 18 over 4. So negative 9 over 4. So that means my particle starts here at 0. It moves over to a point here, negative 9 over 4. And then it travels back again to finish here at 0. So if I want to know the total distance then, we travel 9 over 4 meters to the left and then 9 over 4 meters to the right. So that will give us 18 over 4, or 9 over 2 meters is our total distance travelled. Then if we're wanting to work out average speed, So average speed is equal to our distance divided by the time. Distance divided by time. So that's going to be the same as 9/6, which would give us 3/2 meters per second. Notice that the average speed that we had here is different to our average velocity. They are two different things. Now, one final thing I want to say, it doesn't have it here as a question, but if we were to add an extra question F and find out the acceleration when t equals 3, we would need the acceleration formula. To get acceleration, so we currently have velocity. To get acceleration, we're going downwards, so we have to differentiate. So my velocity equation is this one here. To differentiate, we get just 2. So that means the acceleration is constant. It is always 2 meters per second squared. Or this could sometimes be written like so, but it still means 2 meters per second squared, and that is always the acceleration. Okay, everyone, so those are the applications. That you might find a couple of others in your textbook that you need to work through as well, but those you should be able to figure out yourselves. Have a try, see how you go, and let me know if you have any troubles. Thanks for watching.